In this lesson, we're going to put everything together that we learned for triangles and trigonometry. So we're going to choose a strategy, and that strategy is going to be determined by what is given and what is unknown. The table below here shows us how to decide between sine law and cosine law. Really what you should be doing is drawing a diagram. Once you've drawn a clearly labeled diagram, choosing a strategy becomes much easier, but this table is very helpful. How do we use this table? Well, for the first one, for example, that means we're given two sides and we're solving for the angle opposite one of the sides. The measurement to be determined is that angle, so we use the sine law, and so on. So as long as you have a clearly labeled diagram, you can choose which strategy you need to use. Let's take a look at a couple of examples. In this first example, it says connecting an acute triangle model to a situation. So two security cameras in a museum must be adjusted to monitor a new display of fossils. The cameras are mounted 6 meters above the floor, directly across from each other on opposite walls. So that's here in A and B in our diagram. So those are our security cameras. The walls are 12 meters apart. That's shown here, 12 meters apart. The fossils are displayed in cases made of wood and glass. The top of the display is 1.5 meters above the floor, so that's the height of our display case here. The distance from the camera on the left to the center of the top of the display is 4.8 meters. Both cameras must aim at the center of the top of the display. So what we need to do is determine the angles of depression to the nearest degree of each camera. So alpha and theta. Now, looking at these, I like that I can see some 90-degree triangles or right triangles. That means I can use my primary trig. If I first look at alpha, I think, okay, here's alpha, here's my opposite side, here's my adjacent side, and I'm ready to go. But then I'm reminded that my adjacent side only goes this far. There's another piece here that's included in the 12 meters. 12 meters is the distance all the way across. So I can't actually use that 12 meters to help me out. So then I look here at my hypotenuse, and there's no information there either. So I'm not given enough information to use primary trig to solve for alpha. So let's go over and look at theta and see if that's more useful. So if I go to theta, my opposite side is 4.5. Oh, I don't have the adjacent side, but I do have the hypotenuse, so that's good. The 4.8 is my hypotenuse. Don't get confused by the 6 meters here. Opposite of hypotenuse, that tells me I can use sine. So sine of theta. Plug in what I know. I know that the opposite side is 4.5 and the hypotenuse is 4.8. I'm not solving for the sine of theta, but I'm solving for theta. So to do that, I would go inverse sine of 4.5 over 4.8. All right, let's plug that into our calculators. So second sine 4.5 4.8, and I get 69.64 degrees. Now, looking at our question here, to the nearest degree, so I can round that to 70 degrees. All right, so theta is equal to 70 degrees. I still have to solve for alpha though, so let's erase this other information around. I can put my 70 degrees in here, so that's what I solved for, and I want to get alpha. Now we already saw that using the right angle trig, where we've got our opposite side and our hypotenuse isn't going to be useful because the 12 meters is all the way across. So what if I used, sorry, that was adjacent, not hypotenuse. What if I used the hypotenuse? That's what I was leading us towards here. Now, how do I solve the hypotenuse? Can I solve for the hypotenuse? Let's redraw our big triangle here. So we've got 12 meters all the way across. And then I've got this 4.8 meters. And this goes back up to alpha. I just solved that this was 70 degrees. Now, if we label this A and B, and this was D, right? could we use, or do we have, a tool to solve for alpha? Well, if I've got one side, and I want to, two sides in the contained angle here, right? I've got the 12 meters, the 4.8 meters, and the contained angle. I can solve for this side A by using the cosine law, right? So, go back here, right? I've got two sides in a contained angle, so that would be the cosine law. Let's do that. Oops. So how would that look? Well, solving for side A, I'd have a squared is equal to, this would be d and b, d squared plus b squared minus 2db cosine of angle A. Substitute everything in and solve for A. So I've got a squared, d is 12, b is 4.8, and angle A is 70 degrees. Now if you want to simplify once more, you can do that. Otherwise, you can go ahead and square root both sides and plug that all into your calculator. If you do that, you end up with side A as 11.3 meters. Okay, if you want, I can plug that in my calculator and show you how I got that. So the square root and open brackets, I've got 4.8 squared plus 12 squared minus 2 times 4.8 times 12 times cosine of 70 degrees. Close the brackets there, close the other brackets, hit enter, and there's that 11.3 meters. Okay. If you want to do it in multiple steps, you can, but you can also throw that all into your calculator in one shot. That's actually not what we're solving for. We're solving for alpha, but this is going to be very useful to us. Okay, that was an intermediate step. So now I have that A is equal to 11.3 meters. So going back to our diagram here, I've got that 90-degree triangle, or that right triangle, where this is 11.3 meters. This is alpha. This is 90 degrees here. This is 4.5. And now I have everything I need to solve for that angle. This is opposite, this is hypotenuse. So I can use sine, well, we're not doing theta, we're doing alpha, is opposite over hypotenuse. So sine of alpha, our opposite is 4.5, our hypotenuse is 11.3. To get the angle, it's inverse sine of 4.5 over 11.3. Doing that, we get that alpha is 23.5 degrees. Now again, we're rounding it to the nearest degree. So, right, inverse sine 4.5 divided by 11.3. So we'll round that then to 23 degrees, because I had it 23.5 because it was 4/6. But because it's a 4 first, we would just keep that as a 23 degrees. And there we go. So we've solved for both alpha and theta, but when we were doing that, we had to use some of our primary trig. We had to use the cosine law, right? So you have to go through and figure out what you need. There might be multiple ways of solving this. This is just one way of solving this type of question. Okay. All right, let's take a look at example 2. Example 2, connecting acute triangle models to indirect measurements. Now, there's lots going on in this question. If I look at the diagram before I even start reading it, I can see, okay, I've got some sort of structure, looks like a totem pole. I've got the sun's rays, maybe. I've got an elevated part down here. So I've got a right triangle, but then I've got this other little triangle in here too, making this triangle here, if I outline it, not actually a right triangle. Although there is, if you look with the highlighter, there is a right triangle in here as well. So there's two pieces going on here. So let's see what this question's asking us to do. The world's tallest freestanding totem pole is located in Beacon Hill Park in Victoria, BC. It was carved from a single cedar log by noted carver Chief Mungo Martin of the Kawalakut, I don't think I said that right, with a team that included his son David and Henry Hunt. It was erected in 1956. While visiting the park, Manuel wanted to determine the height of the totem pole, so he drew a sketch and made some measurements. I walked along the shadow of the totem pole and counted 42 paces, estimating each pace was about 1 meter. I estimated that the angle of elevation of the sun was about 40 degrees. I observed that the shadow ran uphill, and I estimated that the angle the hill made with the horizontal was about 5 degrees. So that's this little angle in here, that 5 degrees. How can Manuel determine the height of the totem pole to the nearest meter? Alright, so let's have a look and see what we can figure out right from the start. So if I have a 40-degree angle in here and a 5-degree angle, right, we've got this little triangle here that looks like this. If this is 5 degrees and this is 40 degrees, I can for sure find out this angle. And if I find out that angle, I can find out this angle as well, which would be very useful in our case here, right? So if I take angle ADB, so ADB, that's this one, that would be 180 degrees minus the 40 degrees minus 5 degrees to give us an angle of 135 degrees. Okay, so right in here is 135 degrees. So to figure out this other angle, angle CDB, which is in here, I could take 180 degrees minus 135 degrees, and I would get 45 degrees. So this angle in here is 45 degrees. Now, why is that useful to me? Well, I'm starting to get angle measurements for this other non-right triangle. This 5 degrees here helps me because if this whole angle is a 90 degrees, right, then that means that angle CBD is going to be 90 minus 5, which is 85 degrees. Alright, so this is 85 degrees in here. So if I just redraw that triangle, it looks like this. The totem pole looking like this. And this is my 85 degrees, and this is my 45 degrees. So that means, this is D, this is B, and that top one is C. That means that angle DCB would be 180 degrees minus the 45 and minus the 85. So angle DCB would give us, I could just put it up here, 50 degrees. So now I have 3 angles. I know that this measurement is given as 42 meters. I want to figure out what this height is. Well, now that I've got all of this information, I should have everything I need to solve. If I go back to my toolbox here, I can see if I'm given 2 angles and a side, and I'm solving for a side, then I'm going to use the Sine Law. So let's go and do that. Right? So looking at my triangle here, I'm solving for this side, and I've got two angles and another side. So I've got everything I need in order to set up sine law. So I'd be using c over sine c is equal to d over sine of d. In this case, it would be 42 over sine of 50, and I've got height is what I'm solving for, over sine of 45 degrees. To solve for each, multiply both sides by sine of 45 degrees. So I'm left with 42 sine of 45 degrees divided by sine of 50 degrees is equal to h. Plugging that in, 42 times sine of 45 divided by sine of 50 gives me 38.76, and it said to the nearest meter, so that would round to 39 meters. So our height would be 39 meters. And that's it for today's lesson. What I want you to keep in mind is that every situation you're going to be given, every problem you're going to be given is a little bit different. As long as you've done lots of practice and are familiar with the tools and when to use them, you should have what you need in order to solve these questions. Thanks for joining me today.